Welcome to Tetryonics. In this lecture we'll be covering the quantum geometry of allotropes and compounds. This lecture forms part of the Tetryonics series based on Tetryonics ebook number 3, Quantum Chemistry, available on YouTube and Google+. Following on from our previous discussions on Tetryonics, we've shown the quantum geometry of energy produces the quantum geometries of mass and matter. Specifically, in this case, those of baryons that go on to form the quanta of all elements, deuterons or deuterium when they combine with electrons. Tetryonics in the previous lecture discussed the quantum orbitals and how they result from the charged geometries of matter and periodic elements, along with the development of a new periodic table for all chemical elements based on, again, their charged geometries. We finalized this with a discussion on the complete geometry of all periodic elements and the atoms that they form, and how Tetryonics can reveal this geometry through the application of charge within equilateral mass energies. And again, the previous lecture showed the relationship between the mass energies of matter and the periodic elements themselves. In this lecture, we'll be expanding on these geometries, these physical geometries, and moving into the allotropes and other compounds that form the basis of chemistry as we know it. Obviously, in the case of allotropes, they are just the same element, but with a different physical geometry to how they come together. In this case, we're highlighting carbon. In the box on the screen, we have lithium, carbon and oxygen from the periodic table and their charged geometries for those elements. Around the outside, to the bottom and to the right, we have allotropic geometries for those three elements. Starting at the top right hand side, we can see lithium can also form from three elements or three deuterium nuclei side by side on the same level. We can see oxygen can also be formed in a stable configuration of an S&P orbital, as opposed to the unstable S&P orbitals of periodic oxygen. And finally, you can see the very unique geometry of carbon-12, as opposed to the periodic carbon that normally forms the geometries of diamonds. The carbon-12 geometries at the bottom of this page are in fact graphene or the Buckminster-Fuller carbon atoms that you often see discussed in chemistry and in physics recently. It's the energy or the mass energy levels of these deuterium nuclei making up the carbon atoms that make the various carbon isotopes. And as discussed in the previous lecture, the classical view of carbon-14 having two extra neutrons to account for their mass is incorrect. In fact, all carbon atoms have equal numbers, as do all elements, equal numbers of protons, neutrons and electrons in all their configurations. The additional mass that is measured in molar measurements of these elements is the result of the energy content of their charged fascia. The elements themselves can come together in a variety of ways, as discussed in the previous lecture, but they all interact via the residual E-force or the electric fields or the external electric fields of their constituent quarks, as highlighted here, with red for positive and black for negative charges. You'll note that every baryon shown here has three up and down quarks combinations forming the various structures. In the case of neutrons, it's obviously a down up down configuration. And in the case of protons, it's an up down up configuration that creates the elements. Once they're formed, it creates the deuterium nuclei. Once the nuclei are formed, they then combine through this external 3-point E field of the quarks to form elements. Normally this may be in the case of periodic elements, although obviously they can form allotropic formations as well. The carbon allotropes, there's a number of them as illustrated here. The most common obviously is that of graphene, or the middle version that you can see on this page. You'll note that they all have the same charge geometries, 504 in total. They all have 6 protons, 6 neutrons and 6 electrons. However, their geometries obviously are vastly different from one to the other. And as such, their bonding points, or their ability to form larger compounds, is affected by this geometry. You'll note at the bottom right of this page, or on the right hand side, we've got the energy levels for various allotropes, in this case carbon-12, where we've simply raised the mass energy of the charged fascia of the deuterium nuclei, and then calculated for their mass matters, or atomic masses. Again, as discussed in the previous lecture, we're calculating for a rest mass matter, exclusive of any black body radiation and or any kinetic energies resulting from motion. This then gives us an exact rest mass for each of the energy levels of carbon-12, and as you'll note there, as the energy content, mass energy, increases for the charged fascias from energy levels 1 through to 8, the rest mass also increases, and calculating back for the baryon particles, you'll see that there's an additional calculation. Level 1 starts off as carbon-12. Level 2 energies then create a carbon-13. Level 3 create carbon-14, and so on up the chain. As you add more and more energy, obviously with the deuterium nuclei being rotating quantum converters, the electrons will spin accordingly faster and faster with varying degrees of angular momentum based on the mass energies of the matter that they're bound to. Carbon-12 can obviously form many structures. The most familiar, as I've mentioned, are the Buckminster fullerenes and the carbon nanotubes that are forming a lot of research these days. They do so through their through the bonding points. In this case, carbon-6 can bond with itself to form these patterns, as can carbon-12. In this illustration, we've shown that the graphene combine together to produce a similar structure to the previous one, slightly larger holes. And although this picture illustrates 3 different energy levels, in fact most of the cases they're all the same energy level, being black. The illustration was drawn with the 3 colors so as to highlight the layering between the graphene sheets. Interestingly enough, in the case of graphene, which is conductive, obviously the electrons tend to bind not so much in the nuclei itself, but also horizontally at the top of the nuclei, which will then form a form of bearing. So the electrons act as a bearing between the sheets of graphene. Oxygen allotropes. Obviously oxygen can form in a number of ways, ozone and other molecules like that. You can see a whole variety of interactions here between periodic oxygen and the way it can combine to form other allotropes of oxygen itself. Obviously, as we've discussed, there's also a stable form of oxygen that won't react with itself to form these complexes. The more stable form sits by itself. Just quickly back on that, you'll note at the top left hand corner there's a hydroxide where one hydrogen atom has attached. Obviously in the case of that, the p orbital is short one element, and obviously that bonding point and that element in particular, the hydroxide one, will seek to equalize or fill that p orbital by quickly reacting with and binding to another compound or another element. And this explains why the hydroxides are very reactive. Phosphor allotropes also can combine in a number of different ways. Obviously they have large and filled p orbitals, but as you'll see in this picture here, what's highlighted is the fact that the phosphor allotropes also have 3 bonding points left in the level 3 or energy level 3 p orbital, which allows them to react readily with others. In this case, this is one of the early examples of a ring compound that can form strictly from from similar elements, molecules of the same element, to form a larger one. P6 versus P2. They will initially form as a chain, and then they'll have a preference through their charged fascia to form cyclic compounds and the rest. Sulfur itself obviously can form a huge number of other compounds. As you'll see here, down the bottom we have our chains of sulfur compounds, leaving the positive and negative charged fascia at the end of the chains free for interaction. These can either bond with other compounds to form complex molecules, or they can in fact link back around on themselves and form a cyclic compound, as we just previously discussed. Obviously there's the tetrasulfides and the trisulfides and many other compounds like that. Again, just to stress that the square numbers of energy levels in all of quantum mechanics and physics and in quantum chemistry itself is the result of the square of the equilateral geometries of mass energy, and it's these mass energies and their square numbers that form the charged fascia of all matter, including elements and compounds. As the mass energy increases, as we previously touched on with carbon, the mass of the element itself increases accordingly. And what you see here is a table illustrating the various energy levels of deuterium nuclei as they form larger and larger elements. As the energy levels increase for each of these elements, you can see the corresponding masses as they change. If you then divide these by 45,000 and 12 for each deuterium nuclei, you would be able to calculate quickly how many deuterium nuclei are in these compounds, and in fact the total molar matter for these compounds. Again, as the mass matter increases for all these compounds, there's no additional neutrons to be found in the elements themselves. All the additional mass energy is contained as a raised quantum level in the charged fascia of the matter itself. This is normally indicated in Tetryonics as a coloured charged surface that's available for bonding with each element, in this case hydrogen. Expanding on this, we can obviously show in greater detail the carbon isotopes of carbon 12 to 14 specifically, where we start with carbon 12, 6 neutrons and 6 protons and 6 electrons, which has a molar mass of 11.996 grams. We then raise the mass energy content of the charged fascia to the second quantum level, and we find that we have carbon 13 with a molar mass of 12.985 grams per mole. And additionally, again, if we raise that energy level further one more level to level 3, we would obtain a molar mass for the carbon matter of 14.018 grams. Obviously this has been interpreted as the addition of neutrons to the carbon atoms to create the extra mass. In this case, Tetryonics clearly shows through equilateral mass energies on their charged fascia that that's not the case. The neutral mass energy of the neutron that's historically been used to account for this additional mass of the element is in fact the neutral energies or mass energies of the nuclei themselves and in their charged fascia. We've indicated this here as a polar view as well as a side elevation view of the same elements. And obviously you can increase this level further and further each time, and as you increase it you'll see that you gain extra mass, roughly an extra neutron for each energy level on the way up. If we were to draw a physical representation of these energy levels, as we've just discussed on the previous page, we can see the difference between the periodic carbon and the allotropic graphene or carbon-12. And Tetryonics allows us to draw the physical geometries and mass energy levels of each of these carbon atoms. We can then calculate their mass energies for each of these levels. We can relate that to either Tetryonic mass energies, equilateral geometries, or we can list them as just electron volts or some other suitable unit of measurement. Again, you'll note that all these additional energies for all the non-ground carbon isotopes are listed with neutral colors, because the energy that is being inputted into them come from neutral photons or heat radiation sources in order to raise their temperature. It's a neutral form of energy, and the energy that's stored is neutral, hence why it's always been mistaken as neutrons. It's absorbed in this manner, it's stored in this manner, and it's released normally as neutral, or in the case of sufficient energies you can in fact create particles with the gamma rays, etc. Again, that would require higher energy levels than what we have here, although at level 5 for example you do have the equivalent energy levels here to create substantial particles if you're able to release it all at once and in the create manner. All carbon isotopes in the case of, or allotropes in the case of carbon-12 form this Star of David pattern with an alternating grouping of 6 where there's neutron, proton around in a circular fashion. And again, they can either have the electrons bound into the side of the deuterium nuclei, or they can rest on top in the case of conductive carbon. But in each case you'll see with the numbering there is only one electron, and it is simply the energy level of the deuterium nuclei that raises the angular momentum of the electrons that are bound to the atom. Nitrogen, exactly the same thing again. We have allotropic formations of the elements themselves, which differ from the periodic arrangement of the element. And again, as we raise the energy levels of these allotropes, we can quickly see that the molar mass changes, and using traditional chemistry we would assume that there are neutrons being added to these isotopes or allotropes, isotopes of the allotropic compounds, allotropic elements, when in fact that's not happening. All we're doing is raising the energy levels again of the charged fascia in the matter itself. Oxygen's yet another example where we can raise the energy levels, and we quickly go from oxygen 16 to 17 to 18, 20, 21, 23, 24 and 26. We miss various ones like oxygen 19 purely because the energy levels are such with the geometry that the mass amounts will give us, instead of 60,000 N quanta, we jump to 93. So we miss the amount to make 3. It goes straight to 4. Again, This additional mass energy, normally mistaken as 1, 2 or 4 neutrons, is in fact mass energy in the charged geometries themselves, and each element has, according to its elemental number, that amount of deuterium nuclei, and the same amount of, obviously, protons, neutrons and electrons. Tetryonics gives us the ability, using the charged geometries, to see the interaction points of all elements as they form larger compounds and then fission into smaller byproducts. We can see not only the bonding points and the geometry for each element, we also know from the electron orbitals for each element and for elements in general where the next filling point will be. Obviously in this case the next one will be there to give us a balanced S with a P1 and 2 orbitals, and then it will seek to fill this one and then this one and go on from there. This one will obviously seek to fill its p orbitals and so on. The bonding points in Tetryonics are highlighted according to the color of the mass energies, the color of the mass energies for each element, so you can quickly see what it's seeking to join to and the geometry of the join point that's required. Obviously in the case of these black points are bonding points, and they also reflect a stable p orbital. You can form larger and larger compounds through covalent ionic bonds and hydroxide bonds, but they all seek to form a noble gas configuration or a core electron configuration. Even larger ions like nitrates and carbonates, illustrated here, with very similar geometries, all form from this bonding process. The core electrons are obviously neon, argon, krypton, xenon and radon, all illustrated here with their charged geometries, and they're all examples of stable electron configurations. All the elements under the second law of Tetryonics seek equilibrium, or their most stable configuration, and in doing so they tend to form noble gases, or if they're fractured in the fission process, they will tend to release core electron configurations of noble gases. The gases themselves can be written out in long form, indicating their core electron configuration, where they have helium at their core. Obviously they have a 1s2 configuration, and then the deuterium nuclei form around that core to create larger elements. This will continue up until they reach a stable configuration with helium, and then you'll start to have d orbitals, electron orbitals, filling up with your transition metals and the like. As it fills up, obviously in this case the energy levels are raised as it seeks higher energies and larger elements, and here you have the d orbitals being formed for krypton. So krypton has a core orbital, a core noble gas of argon, and around it then has additional deuterium nuclei to form the stable d orbital configuration of krypton, and this just continues up and up. Tetryonics Quantum Chemistry lecture gives you the full breakdown of how all these elements come together, and then the short video and the quantum chemistry ebook itself have individual pages for each and every of the 120 possible periodic elements that can be formed, along with their physical geometries and chemical properties and their position in the new periodic table. There exists numerous other forces that have been described in chemistry to account for interactions, like the van der Waals force. Obviously, Tetryonics has to account for these and show the interactions. They are simply the charge interactions, similar to strong force interactions that hold quarks together in the deuterium nuclei, but slightly weaker because due to the fact that the geometry of the physical geometry of the deuterium nuclei will not allow these charged fascia to come in direct contact with each other like they do in the case of quarks within the nuclei itself. They're held apart because when you build the models of the deuterium nuclei and look down at them from the top, you will soon discover that the top surface is a hexagon, the bottom surface is a pentagon, and this irregular shape highlighted here in light grey, for those that will be able to, when you download the book and look at it in great detail, the light grey shaping around the outside is reflective of the two different geometries, and you'll find that when you go to build the atoms, they won't come together in contact between their charged surfaces. Between the charged surfaces where the electric field of the quarks is combined to form the residual E fields, they are held apart by this subtle change in geometry. The Lewis structures, familiar to all chemists that have done chemistry for the last probably 2 or 3 centuries, can now be shown to be a close approximation, and in many cases reasonably very accurate, to the actual physical bonding of the elements as they come together to form larger and larger compounds. As given a few illustrations here or examples, you can see the bonding points as they seek to form a stable core configuration by bonding with other elements. They come together via their charged geometries and their quark E fields or residual van der Waals forces to form more larger and more stable compounds. The core electron configurations that we've mentioned have been drawn schematically here, but to scale you can see each of the core electron configurations from deuterium, helium, right through. You can see how these are reactive and they're seeking to form a stable configuration as highlighted in the middle, whereas the core configurations themselves all have filled p, d and f orbitals, and by virtue of them being filled they're stable and inert. So they're your the core electron configurations are your noble gases. In this case the only difference being that Tetryonics shows that instead of hydrogen we in fact have deuterium, as deuterium is the building block of all the elements. Hydrogen is element 0 now, as defined by Tetryonics. It has no neutron with it, it's just an electron and a proton, and it should be excluded from the periodic table of elements. It's a separate element all to itself. Again, as mentioned in the previous lecture, the excess neutrons that are normally drawn with all the elements or pictures of elements in chemistry up till today have been replaced by the Tetryonic geometries, their charged geometries, with their physical mass energy levels highlighted in various colours matching the colour code of the spectral lines. In doing this and explaining the extra mass energies contributing to the total relativistic mass in grams of each element, we can show that the neutron-proton line is in fact a straight line, as all elements are deuterium nuclei. The excess neutrons that are normally calculated as being in the element configurations for periodic elements that are unstable in fact do not exist. What's really happening is that the mass energy levels, the differing mass energy levels of each deuterium nuclei affect the angular momentum of the electrons that are bound to them through their chem fields. These deuterium nuclei act as quantum synchronous rotating converters. The electron will always spin in accordance at a rate that's in accord with the energy level of the deuterium nuclei to which it's bound. And this is the basis of our quantum jumps, our spectral lines, all those sorts of things. If all these deuterium nuclei were the same energy with excess neutrons around it packed in, firstly you wouldn't have the ability to bind them all in the case of elements above element 60, because you'd run out of positive and negative charge binding points. But if you were able to build it with all the elements around and they were all the same energy level, you would no longer have transitions between these energy levels in the atom, because they'd all be identical energy levels. In fact, the current math, or quantum math, of quantum chemistry and molecular chemistry shows this, and it's clearly stated in the math itself at the various quantum levels. But the model of elements and chemical compounds hasn't kept pace with the math and followed what the math says with a formal geometry, and that's what Tetryonics provides. It provides us a geometry of mass energy, or equilateral mass energies, and through the charges of these mass energies we can create the physical charge geometries of all elements and all compounds, when in fact we will never be able to see these elements in reality. Tetryonics obviously has a way of illustrating all its bonds. In the case of hydrogen bonds, they're marked with their various colours on the external fascia of the hydrogen, which then can go on to bind into various free positions in the element if they have sufficient energy levels. You'll note in this case the energy level that has to be filled in the water molecules is a N2 energy level, so energy has to be inputted for this to raise the energy levels of the hydrogen so that they can bind at this energy level to form a stable electron configuration. Obviously they can also come together fascia to fascia, or as closely as to fascia as they can through the London or van der Waals forces, or weak strong force, however you wish to term it. These bondings, facial bondings, create diatomic bonds between elements such as hydrogen in this case to form diatomic hydrogen. They can obviously come together in larger groups through their various charged fascia to form repetitive patterns for your periodic elements and the like, or as they're described here as interfacial bonds. And then obviously as an element themselves they have free positions where they wish to fill in order to create a stable electron configuration or a stable energy configuration. And in doing so they're obviously termed molecular bonds, because they're seeking to form a stable compound or a stable molecule by filling these bond points. You can see on this page a whole range of different bonding points and different free points that still remain. Oxygen, a diatomic oxygen has 4 bond points that remain that it will seek to fill. Hydrogen sulfide, even though it has a stable core configuration, still has spare bonding points where each of these oxygen atoms will seek to fill these points by reacting or combining with other molecules. Obviously when they reach their stable s,p,d orbital configurations, chemistry has a term for describing the electron configurations of these stable elements and compounds, and they refer to it as the valence electrons of these compounds. Normally it's the highest energy electrons in the element, or the most reactive outer elements, electrons of the compound. In the case of bromine, obviously you have N4 energy at the top here, electrons, and you have N3. The N4 are more reactive and have higher energies, able to be liberated or excited away from the element quicker and easier, because less energy is required due to their higher energy state in the first place. But at the same token, these lower N3 energies, electrons, can also react and break away and be excited or react with other elements. Obviously in the case of bromine, it will always try and seek to fill this p orbital, which again makes it very reactive. As in the case with bromine, you have phosphorus, you have 3 reaction points, so it's even more reactive. And it's always seeking to fill these points to create a stable compound, or to get rid of the excess energy that's stored in these N3 level configurations. The valence bonds themselves obviously facilitate this interaction as they seek to form stable electron configurations. In this case, the oxygen will seek to add 2 hydrogen to form a full p orbital, or it can add a hydrogen in this spot here, and it creates a hydroxide, which will then react with something else in order to seek and fill this spare position and create a stable configuration. Again, this is the configuration it's seeking. It's got a full s orbital and a full p orbital. In this case, it's a water molecule. Over here we have fluorine with hydrogen. The hydrogen will bond very quickly to form hydrogen fluoride and create a stable electron configuration. Again, a lot of the lower elements will seek to form this pattern of 8, this core electron configuration, where all the electron orbitals are filled and you have a stable s and p orbitals. Obviously, this filling of s and p orbitals can occur in a whole host of elements, particularly those at the bottom end of the periodic table. They again are all seeking to fill their almost empty s and p and d orbitals, and the d's and f's, or d's and f's in this case of helium and mercury. They're all seeking stable electron configurations. As you get to the larger elements, obviously these stable electron configurations form the core electrons of these elements. And you can see that obviously in the case of mercury, helium, you have a core configuration of a higher energy level, and around that you have less tightly bound deuterium nuclei of a lower energy. So you can either react with the higher energy or excite the higher energy electrons away from this element, and these two will be the first to go, followed by these core ones. Or you could initiate a fission of these elements due to their unique geometry and break away these less tightly bound deuterium nuclei, which will then go off to form helium nuclei if they're captured over a period of time, and that forms alpha decay. Again, even though they have higher energy levels, and that's part of their elemental properties and as a periodic element, what they are seeking to do is either they're seeking to reach a stable electron configuration or stable filled orbital configuration, and they do this by either capturing free elements that can then give them this and they turn into a slightly different element, or they simply bind with other elements in the same environment, seeking to create this stable configuration. In this case, we can see the ionic bonding going on, where a sodium element will give up its N3. You can see all the S and P orbitals are all filled at N2 levels, but N3 is high, so this is the easiest valence electron to break away. It gives up this N3 electron, which once it gives it up, the angular momentum of its bound position becomes a linear momentum, and it drives it away. It then, in doing so, turns it into a positive ion. This in turn can obviously attract a negative ion in chlorine. The N3 can obviously bind with the neutral chlorine atom because it's an N3 level, it binds, gives a negative charge to the chlorine. So by giving up the N3 electron here, this has become a positive ion. This has then captured that N3 electron and created a negative ion with the chlorine. These two then seek to bind. They do so. They are already stable electron configurations. So uniquely, well, not so uniquely, you'll see this pop up quite a few times in chemistry. These two elements simply join together side by side through their charged fascia. You'll see that the bonding points are there and there, because obviously bound electrons won't be able to bind where the bound electrons are, because they will clash and it won't be able to happen. These are in fact spinning at all times. So you have two binding points on both charged ions. They're attracted. In this case you've got negative positive, and you have a negative positive, you have a positive negative, and a negative positive. So these charges will create a torque and an attraction, coulombic attraction, between these elements as they follow the second law of Tetryonics and seek equilibrium, and it will draw them together until they bind. Once they bind, obviously the positive and the negative charges become our neutral charge. Again, it's reached equilibrium. In this case, a salt molecule, as illustrated here in the block diagram. In this case we have a stable, even though it's a neutral charge, we have a stable molecule where one half of the molecule is basically at an N2 or N1 N2 energy level, and the other half is at a N2 N3 energy level, the chlorine. And this difference in energy level also facilitates bonding with other elements and will drive other chemical processes using salt. The octet rule, I won't go into a great deal here. A lot of it is explained on the right hand side of the page. It was a pattern that was noticed using Tetryonic geometry. Basically it goes that you have the s orbitals and the p orbitals form 8, i.e. an octet, where you have no more valence positions available, and then you can build on that with your d orbitals. They still follow obviously sp, d and f orbitals of all electron configurations in periodic elements, and in fact that's exactly what I've used here. But in what I've done here is I've highlighted the number of free electron positions. In this case you have 7 valence electrons. There is one free spot, so it will seek to fill that spot with an extra electron or another compound to bind in that spot there, so that becomes a stable configuration of 8. And you see this over and over, which is why the second law of Tetryonics is worded the way it is. The energy, be it charge energy or be it mass energy, geometries, always seeks equilibrium or the most stable configurations in the journey to finding a low energy state. And this applies to electron transitions, it applies to mass energy itself, it applies to charge geometries, even applies to stellar processes such as stars themselves. All energy in the universe is in motion seeking equilibrium. Again, the octet rule, simply showing here how various molecules are examples of elements elements seeking equilibrium. Methane has 4 hydrogen around the carbon. Hydrogen fluoride, the fluoride bonds with the hydrogen at the same energy level to create a stable electron configuration. If you were to try to bond that, or even water, with lower energy hydrogen, they wouldn't bind at these points. They would in fact be at a lower energy level, physically lower, and it wouldn't bind. There is no binding points left at the lower energy levels, so the energy has to be raised in these hydrogens in order for them to bind into these positions. But once they do, you create a stable compound. A few examples of different compounds out there, obviously water, hydrogen chloride, carbon dioxide, methane, salt again. You can see it here without all the writing on it. You can see the spare bond points. As you become more and more familiar with Tetryonics, you'll quickly see these patterns over and over, and due to the colouring and the geometries, as you become familiar with the filling sequence of sp, d and f orbitals, you'll quickly be able to calculate where the next bond point is and at what energy levels it should be in order to reach a stable compound or elemental configuration. Again, more complex, obviously in this case highlighting larger bondings of elements into bigger compounds than previously. Note the similarity between the nitrate ions and the bicarbonate ions. It's always been known that they are very similar in geometries, and in fact you can see this repeated here. They are identical so far as the physical geometry goes, even though they are quite distinct chemical formulations. They've come together from different periodic elements to create these identical structures with identical bonding points. And this continues right through larger and larger and more complex compounds. We'll quickly run through a few of the more basic compounds here. Obviously, as we've discussed, two hydrogen atoms are made up of protons and electrons. They have a net neutral charge, however they can still bind, as we've mentioned, through the residual E-force of the charged fascia of their quarks. In this case, the down quarks and the up quarks can come together within the protons themselves, as illustrated on these polar diagrams, and they form the diatomic hydrogen gas molecules. Again, they're neutral particles. Classical chemistry has trouble explaining why neutral particles can be attracted to themselves. Tetryonic obviously shows that even with neutral particles, they are comprised of positive and negative charges, and particularly their external fascia. And it's this imbalance of positive and negative charges at all levels of physics that drives motion. But always they will seek to form neutral particles. Oxygen's no different. It can bind in a number of different orientations with itself to form diatomic oxygen molecules. And in this case, the diatomic oxygen, O2 molecules, obviously have additional bond points free for reaction with other molecules or binding with other molecules. Carbon monoxide, same thing again. The carbon atom binds with the oxygen atom as it seeks equilibrium. Tetryonics allows us to show the individual elemental particles that come together along with their mass energies and geometries, and allows us to calculate the final charge geometries, and if we wish, the mass energies of these molecules at any of their respective energy levels, or with or without their black body or kinetic energies. Carbon dioxide, same thing again. One carbon, two oxygen molecules forming together, seeking a stable or lower energy state. Nitric oxide, again, just more examples of the plethora of various chemical interactions that can take place once you form matter geometries out of charged mass energies. Nitrous oxide, completely different structure to the previous nitric oxide. You can see it's two different forms. This one has oxygen with nitrogen either end. This one has the two nitrogen binding together with the oxygen at the end. Different configurations. This one has 1, 2, 3, 6 binding points available for interactions. And this one has again 6, but a different arrangement of those 6. We can continue. Here's another example of boron trifluoride. where the boron molecule element has combined with fluoride ones that are all seeking stable configurations. In this case, the boron is binding in here. You can see it trying to seek its p orbital stability, not achieving it, but in the same process the oxygen is still free to react with other molecules. And again, as you physically make these models and or use computers to rotate the molecules about, you'll find there are only specific geometries that will allow these interactions due to the charged geometry of the charged fascias of each molecule. They can only come together in certain ways, and they always follow the electron configurations of the sp and d orbitals. You don't often get F. So all of the Mendeleev table of periodic elements is not only shaken up and replaced by tetryonic geometry in the case of periodic elements themselves, but we in fact can replace the entire structure of Lewis diagrams and the rest, and develop a software package where we use the physical geometries of 3D charged matter. And we can use these geometries to create more and more sophisticated quantum chemistry programs and models of all the elements up through and including viruses and the like, so we can develop chemistry on a quantum basis at a far more rapid pace than has ever been the case before in human history. Obviously, once we do our basic chemistry at the quantum level, we can continue this chemistry and the charged interactions up to larger and larger molecules, including the cyclic molecules of organic chemistry, which is a more difficult subject, but easily described using tetryonic geometries. You can see here the carbon ring, oxygen carbon rings, and nitrogen carbon rings that form the backbone of organic chemistry. And again, tetryonic geometry agrees closely with current chemistry Lewis diagrams and all the other diagrams for organic chemistry. The only difference being that in the case of Tetryonics, we don't have just schematics or schema of lines and compound names or symbols. We have physical geometries showing our charge interactions and the quark interactions and the charged fascia interactions of each molecule as they come together to form these compounds. We'll run through a few here just to show, in the first case, the hydrocarbons, obviously starting with methane, where the carbon atom is sought to achieve a stable electron configuration by adding 4 hydrogen atoms of energy level N2 into its configuration. It binds with these, seeks a stable configuration, and forms methane. Again, Tetryonics can give us the matter geometries highlighted in green, the charge geometries showing that it's a neutral charge once they've all bound together, and can show us the energy levels, allowing us to calculate the mass of each matter geometry that's formed through these compounds that are formed. We can make ethylene. We can draw the picture of ethylene. Obviously, we can show its binding points between the carbon atoms. We can show where the hydrogen binds in and how it begins to form a chain structure. We can show ethane with the additional hydrogen the hydrogen bonds, and obviously the fact that it is the same size, although it has additional hydrogen bonds, hydrogen atoms. Butadiene, these elements just continue. I'll quickly go through them. Propane. You're welcome to go back at some time and either view the individual illustrations that I'm showing you here, like butane. Check that there's the right amount of carbon for hydrogens, and that the actual physical, in this case we'll see CH3, you see a carbon with 3 hydrogen, you'll see a CH3, again carbon with 3 hydrogen at the end, and in the middle you see 2 CH2s. We have a carbon, 2 hydrogens, carbon, 2 hydrogens, all linked together to form butane. This pattern will repeat. Again, I encourage you to build the models physically yourself, as I have, and you'll get to see the interaction points and how the magnetic fields along with the electric fields play different roles within organic chemistry itself. Obviously all these particles are neutral particles. Pentane, again you can check the element configuration, the chemical formula, and you'll see that it is mirrored in the actual formation of the element pictured here using Tetryonics. Hexane, these elements get larger and larger. Heptane, obviously, hence their names. They're all carbon and hydrogen compounds, hence the name hydrocarbons. And they're the backbone of all organic chemistry. Octane, again, you can see it's a neutral compound. It has 4,896 charged fascia in its matter. And if you wished, you could sit down and do the quick calculation using the masses that are indicated there with their energy levels, and you could calculate the exact rest mass of the octane matter. Obviously different compounds can arise, like ethanol, trihexane, and it might be trishexane, cyclohexane. You can see that in fact this could be redesignated. Instead of a cyclic, it could actually be just a double chain held together with a hydrogen bond. And onwards and upwards till you get to things like benzene. Obviously as the chain gets larger and larger, you obviously have, if there are no hydrogen bonds at the end of these elements, you have free bonding points available for other elements to bind in and attach to them to give us a lot more organic compounds. But in addition, these binding points at the end, you'll note that you have 2 protons here and 2 neutrons at this end. Obviously these charged fascia negatives are seeking a positive, and this positive fascia bond point here is seeking a negative. So left to their own devices, they can be chains of hydrocarbons, but in a collection, a lot of these positive and negative bond points will either link to others to form longer chains, or they'll link to themselves to form cyclics, as illustrated in this top picture here. Again, just repeating what we've said, we've had 6 carbon atoms here in the carbon chains. They come together and bind at these points here through their positive and negative charged fascia, and in doing so, while they continue to seek a stable electron configuration, they also have these free charged fascia for interactions, and they again will form a cyclic compound. Not really well illustrated here in Tetryonics handbook and in the ebook itself, because of the inability to draw 3-dimensional diagrams on a 2-dimensional page. They can form this way, and if you were to cut this picture out of the page, if you printed it and cut it, you would then be able to fold it up into a circle. Form a circle where this end attaches to that end, and you'd have a cyclic chain. Additionally, you can take periodic carbon, and it will in fact chain up as a polar view in this manner as well. Obviously you can replace one of the carbon atoms in the chain with an oxygen atom. Again, forms a different cyclic, in this case an oxygen carbon cyclic, with different properties obviously and different bond points. Similar but different. These compounds can then obviously then seek stable S&P orbitals, as will the molecules that are around them, and it is through this seeking of equilibrium and the charged fascia that these compounds will come together to form larger and larger organic compounds, as you can see here. Obviously the carbon rings themselves can interact, and they can bind with themselves, as we gave you an example of early in the beginning of this lecture, where we showed you the graphene interactions, as well as periodic carbon itself forming compounds. In this case we have the periodic carbon forming a cyclic ring, binding with hydrogen atoms, and then these hydrogen carbide rings then bind together through these connections here and form these distinct patterns with very strong bonding. You'll find a whole chain through here. You've got a 3-layer binding here that results, as opposed to just the single staggered 1-2 binding of the individual chain carbon hydrogen rings. Obviously, if these hydrogens weren't there, then these binding points, reaction points, would then be free to accept other molecules of the right energy level. They all have to be obviously N2 or higher. If a higher energy one was to bind with these in these bind points, obviously the mass energies of say N3 that bound here would seek to spread out through the carbon rings, would seek to equalize this energy and spread the mass energy out. Again, apart from just periodic elements themselves, the physical geometries of all elements can be represented and drawn with Tetryonics, up to 3-dimensional ones on 2-dimensional paper. Obviously, as we develop again over time, we will develop software that will physically model these geometries in real time on the computer, and we'll be able to go away from all our traditional chemical diagrams and illustrations and use purely Tetryonic geometries for all our chemistry and all our studies of molecules, viruses, organic sugars, the rest. And speaking of sugars, we now move into the carbohydrates, obviously listed here, all following a similar formula, just like the hydrocarbons, but in this case we obviously have m amount of carbon molecules attached to a water n amount of water molecules, creating our carbohydrates as opposed to the hydrocarbons. These are normally called sucrose, glucose, lactose and dioxys when you build into the DNAs. Obviously starting with the monosaccharides, which are just a CH2 general compound structure. You can see this structure here as illustrated. They're just chains of carbon, oxygen and hydrogen coming together through their various charged geometries, seeking stable orbitals and equalized energy levels. In this case they all tend to be at N2. I have, in the case of carbon, or oxygen, made the oxygen one a slightly lighter orange, just to help differentiate between the carbon and the oxygen in the picture. Otherwise it becomes a bit difficult to view it and see the difference of one to the other. The monosaccharides can obviously then bind together through their charged fascia and the Lewis or van der Waals forces, and combine, seeking a stable electron and energy configuration. They bind as a disaccharide instead of two monos to make a disaccharide. This then ejects a stable water molecule, oxygen plus 2 hydrogen, from the disaccharide energy configuration to give us a condensed disaccharide and obviously the water. They can obviously come together with your carbon and your oxygen and hydrogen, noting again that Tetryonics shows you specifically where they combine together through their charge fascia and through their electron positioning, where electrons to be in positions where a chemical or an element would want to bind, but the electrons there would prevent that binding. Or if two elements come together and the electrons clash, obviously that binding point is unavailable. But in doing so, they again, just like hydrocarbons, form chains. They can be chains of carbon or other molecules, but in this case we've got the monosaccharides coming together, and we have a carbon chain in the middle, again with 2 positive charge fascia and 2 negative charge fascia at each end of this chain. And these chains will actually, if you were to cut it out, would fold around and bind together. They can form longer chains by linking together, or they can form cyclic chains. Again, you can have mirror images of one molecule or the other, just depending on which way these molecules come in for their interaction with the carbon. These chains can continue to develop, adding more and more oxygen, more and more hydrogen, to form larger and larger sugars. As you'll see here, the chemical formulas will match if you sit down and work it all out. It's all there. And this just continues and continues into the polysaccharides and even through into DNA, as you'll see. The polysaccharides, very large complex chain, large chemical formula, straightforward though. Again, it's always seeking equilibrium as it forms. Again, we can show in the case of polysaccharides it's N compounds coming together, each compound having 6,864 charged fascia. All of a neutral charge. Again, the neutral charges still interact through their charged geometries, and they link up to form chains one after the other. You can see there's 3 of them here that have joined in their chain configuration with their cyclic compound structure. They have these free bonding points, and this one here will obviously seek to bind with another or some other compound for stability, as will this one. Again, large compound made out of hydrogen, carbon and oxygen, following a generalized formula for polysaccharides. And obviously in this case, the final Tetryonic geometry still mirrors that of current chemistry, Lewis diagrams and the rest, even computer generated diagrams like that. From there we can obviously create ribose compounds with your hydrogen, carbon and oxygen. A more complex chemical formula, but all the same, easily drawn with Tetryonic geometry. And again, you can see the carbon chain forming its backbone with its binding points. These will obviously like to form a cyclic sugar, as most carbon or chains do. They will try to interact either to form longer chains, or they will form cyclics, depending on the density of the atoms or how many molecules are around them with charged fascia for them to interact with. Obviously you can bring 2 of them together and you can form deoxyribose, as illustrated here. It's the one of the major components of DNA. Again, huge chemical formula, straightforward and easily recognizable organic formula using Tetryonic geometries. And again, you can see right down to the quarks of each component deuterium and their binding points, and obviously their charged fascia for interactions. Obviously with the deoxy previously described, we can add a phosphate group. We can develop the phosphate group using Tetryonics, and we can show the binding point of the phosphate group to the deoxyribose compound. We can show all 4 DNA bases for DNA itself, the physical geometries of each one. As you can see there, their charges, their charged geometry. We could calculate their mass of each individual DNA base, but more importantly we can see their physical geometry, the lengths of each DNA base. As some are longer than others. We can see that they have positive and negative charges at the end of their chains. Again, these positive and negative charges are points that will seek equilibrium or seek to bind with other compounds as they seek equilibrium. Traditionally they're drawn completely differently. Again, they're trying to represent a 3-dimensional diagram on a 2-dimensional page, as is Tetryonics. Tetryonics shows you the physical geometry and the binding points for each of these DNA bases. Obviously these DNA bases can then interact via their positive and negative charge ends on their chains. They're obviously already attached at one end to the phosphate groups, They then leave the other end free at each end here to bind positive or negative with another DNA base, and that's precisely what they seek to do. These positive and negative bases, if you imagine the deoxyribose being bound here, still has the positive and negative free. Again, we have a bind point here on cytosine with a negative and a positive. The guanine has a dioxy bond point here with a positive and a negative still free, and the adenine has a negative and a positive. You'll note that there are specific positive and negative orientations to these DNA bases, and it's these DNA base charge orientations that dictates they can come together. You'll see that a C or an A with its two positives, if you were to move it down, would not bind with a C because the positive charges would repel each other, and likewise the G could not bind with a T because the negative charges would repel. So in fact the A's will bind with T's, G's with C's, and vice versa. C's with G's, T's with A's, and this forms the backbone of the linking of DNA double helixes with the base pairs between them, between the spirals itself. The phosphate groups form the spiral or the ladder itself, with the DNA base pairs forming the rungs of the ladder as they come together through these charged fascia to form a larger chain, AT GCs or GCs TAs, as illustrated here. We have them coming together, again remembering that they have specific positive and negative charges. A lot of textbooks will claim that the interaction between these base pairs is that of a hydrogen bond. In fact, it's at the quantum level, it's a deuterium bond between the deuterium nuclei that make up the element in the compound that forms the base pair. But in fact, it is the charged fascia between the deuterium nuclei that's facilitating the interaction and creating the binding. Again, the binding itself is only a weak fascia charge, a London's or van der Waals force, residual EM force if you like, and can be easily broken. It's not, even though it's the same mechanism, electric charges on fascias, it is not a strong force interaction. It's a residual E force interaction again, as 99% of all chemical interactions or bonds are. But again, Tetryonics takes there's a simplified view here of the carbon with the various compounds. You can compare this page to the previous page to see that these compounds do in fact reflect the tetraionic geometries. They are a simplified version just to make it easy to see, and you can see how the two carbons will come together, or the deuterium nuclei, the charged fascia between them, will come together to form a large chain which forms the rung of the DNA helix. Having covered all that, we've just about finished quantum chemistry. Obviously there'll be another lecture to finish the discussion on the quantum chemistry book of Tetryonics, and that final lecture will be fission. We won't cover it here. We'll finish up and we'll discuss fission in a separate discussion in another lecture.